From the moment we open our eyes and begin to make sense of the world, we are taught that reality is made of solid things. The ground beneath us feels firm. The walls surrounding us resist our touch, and every object appears to have its shape and boundaries. It is natural to assume that at the smallest scales, these things must still be tiny solid marbles, unyielding and compact, packed tightly together to build the universe. But the deeper science has looked, the stranger the picture has become. The solidity we take for granted is an illusion woven by forces and probabilities, not by miniature billiard balls locked in place. Everyday physics belongs to the realm we call classical. Here, objects follow predictable rules. A ball thrown into the air will trace a smooth curve. An apple dropped from a tree falls with acceleration determined by gravity, and a pendulum swings back and forth with measurable rhythm. We can measure, calculate, and forecast, often with astonishing precision. If you tell me the speed and angle of a cannonball, I can calculate where it will land. If you describe the weight of a bridge, I can tell you how strong its supports must be. In this world of our senses, cause and effect unfold in ways that feel logical, even comforting. But shrink yourself down, not by meters or centimeters, but by trillions of times. Dive past molecules and atoms, beyond the nucleus of protons and neutrons, and you arrive at a domain where those classical rules collapse. Here, electrons do not orbit like tiny moons circling a planet. Instead, they exist as clouds of probability, hovering in regions where they might be found if observed. Light does not behave as a simple wave or a simple particle, but as both, depending on how you look at it. And the act of looking itself is not passive. Observation changes the system, collapsing the possibilities into a single outcome. This is the quantum world, where emptiness is not truly empty, and where certainty gives way to chance. Particles are not neat points with fixed properties. They are excitations of invisible fields, ripples in the deep structure of reality. A single electron is not a speck moving along a definite path, but a smear of possibilities, like a ghost that can be in many places at once until measured. In this domain, probability is not a tool for ignorance, as it is in everyday gambling. It is the fundamental fabric of what exists. Consider the atom. Most of its volume is nothing at all. If the nucleus were the size of a marble, the electrons would be buzzing around far away, and the space between them would stretch out like a cathedral, vast and hollow. Yet when you press your hand against a table, it feels solid. That sensation does not come from atoms truly touching one another. It comes from the electromagnetic forces that resist the overlap of electron clouds. What we call solidity is simply resistance, an interaction of invisible fields that convinces our senses of a firm surface. Reality, in truth, is mostly space and probability, stitched together by forces that our eyes cannot see. In this strange theater, something even more remarkable emerges. Quantum mechanics allows particles not only to exist in many possible states, but also to link together across space in ways that defy ordinary logic. Two photons, born from the same event, can share a single quantum state, no matter how far they travel apart. Two electrons can spin in opposite directions as though connected by an invisible thread, even if they are separated by kilometers. The moment you measure one, the other seems to know instantly. This is not a trick of hidden wires or delayed signals. It is a genuine property of the quantum world, where separation itself seems to lose meaning. Einstein once looked into this abyss and recoiled. To him, reality was local, sensible, and complete. Yet here was a prediction that suggested nature could stretch across space with a connection faster than any signal could travel. He called it spooky action at a distance, a phrase that has echoed across generations. What Einstein could not accept at first is what experiments now confirm. Entanglement, as we call it, is real. It belongs not to science fiction, but to the foundation of quantum theory. And so, As we leave behind the comforts of classical certainty and step fully into this quantum world, we prepare ourselves for the most unsettling journey in physics. A journey where particles share a single existence, where the act of observation reshapes reality, and where distance itself may be little more than an illusion. Within this strange realm, Einstein encountered something that seemed to mock the very limits of understanding. He encountered the beginning of the story we are about to unfold. The quantum world demands patience because it does not reveal itself in ways that match our instincts. For centuries, humans trusted their senses, guided by the belief that what we see and touch reflects the deepest structure of reality. But the microscope of mathematics and experiment revealed that beneath the surface lies something utterly foreign to common sense. In the early 20th century, pioneers such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger forced themselves to abandon familiar notions of certainty. They discovered that the quantum realm was not governed by smooth trajectories and predictable clocks, but by wave functions, those strange mathematical expressions that encode probabilities. Imagine tossing a coin. In our ordinary world, the coin spins, and though we may not know the outcome until it lands, the result is already decided, hidden in the motion of the spin and the influence of the air. If we could measure everything precisely enough, we could know the result before it falls. But in the quantum world, the coin truly exists as both heads and tails, neither fixed until the moment of measurement. When you finally look, the wave function collapses and the coin chooses. Until then, the universe holds both possibilities in superposition, a shimmering overlap of realities. This is not merely an abstract idea. Double-slit experiments with electrons, performed again and again, reveal interference patterns that only waves can produce, until the moment of observation changes the story. When watched, the electrons behave like particles, passing through one slit or the other. When unobserved, they act like waves, spreading out and interfering with themselves. The difference is not in the electron, but in the act of measurement. This is one of the most unsettling lessons of quantum mechanics, that reality itself may be participatory, called into sharp form by our acts of observation. In this world, emptiness itself shimmers with possibility. What we think of as vacuum is not barren nothing, but a restless ocean of virtual particles, flickering into existence and then vanishing in unimaginably short timescales. Even the darkest reaches of space between stars are alive with this activity. This restless quantum foam may hold the seeds of the universe's structure, for out of it arise the fluctuations that shaped galaxies, stars, and planets. The void, far from empty, is a seething backdrop to all that exists. And yet, within this quantum sea, the rules are precise. The uncertainty principle, revealed by Heisenberg, dictates that one cannot know both the position and momentum of a particle with perfect accuracy. The sharper you pin down one, the more the other slips away. This is not a limitation of our instruments, but a built-in feature of reality. Particles are not objects with well-defined paths waiting for us to measure them. They are inherently uncertain. They're being stretched across ranges of possibility. Think of a violin string vibrating. It can resonate in many ways, with overtones and harmonics. In the same way, an electron around an atom does not occupy a single orbit, but a cloud of allowed states, a quantum symphony of probabilities. Each energy level is like a note that the atom can play. When an electron jumps from one level to another, the atom emits or absorbs light, and the colors we see in stars are written by these transitions. The richness of the cosmos, from the red glow of hydrogen to the golden light of our sun, is painted by the quantum rules that govern these tiny transitions. As unsettling as this world is, it is not disconnected from our daily lives. Quantum mechanics underlies the technologies we use constantly. The semiconductors in our phones, the lasers in our devices, the medical imaging machines in hospitals, all depend on these strange principles. Without the uncertainty principle, without the wave function, And without superposition, modern civilization would not look as it does today. The very fact that you are hearing or reading these words through electronic devices is evidence that the quantum world is not a curiosity, but a foundation. But entanglement is the phenomenon that truly shakes our sense of reality. Superposition already teaches us that a particle can exist in overlapping possibilities. Entanglement extends this strangeness to two or more particles, weaving them together so completely that they cannot be described independently. When you measure one, you immediately know the state of the other, no matter how far apart they are. Their connection is not through space, not through time, but through a shared quantum state. It is as though reality insists they are one system, even when separated by vast distance. This is where Einstein drew his line. For him, relativity demanded that no influence could travel faster than light. The cosmic speed limit was absolute, a cornerstone of his theory. Yet here was a prediction of quantum mechanics that seemed to allow instantaneous connection, action, at a distance, without any signal. To Einstein, this meant that quantum theory must be incomplete, that some hidden variables must be lurking beneath the mathematics. He could not accept that the universe itself would play dice and weave such uncanny threads. But the mathematics and the experiments whispered a different story. They showed that the universe does not bow to classical expectations, that entanglement is not a mistake, but a feature. Before the tests were complete, the question hung like a cloud over physics. Were we missing hidden pieces, or was the universe stranger than even Einstein dared to believe? And so we stand at the edge of this first revelation. The quantum world is not a smaller version of our classical world. It is a realm with its own rules, rules that demand we abandon our assumptions of solidity, certainty, and independence. In this new landscape, entanglement becomes possible, a doorway into the most profound mystery of modern physics. The deeper one lingers in the quantum world, the more the ordinary notions of separation and individuality seem to dissolve. A grain of sand, a breath of air, a spark of light, all appear to be made of distinct entities. But peel away the familiar scales, and you find that these so-called entities are patterns in a field, ripples of probability, endlessly shifting until measured. It is here that quantum entanglement emerges not as an oddity, but as a natural extension of the principles that govern everything beneath the surface of the visible world. To feel the weight of this transformation, picture an ordinary classroom globe. You spin it, point to a location, and you know precisely where you are on its surface. This is the classical expectation. But a quantum globe would not permit such certainty. Before you look, the globe could exist in many overlapping states, its pointer smudged across every longitude and latitude at once. Only when you touch it with observation does it settle into one. This is strange enough, but entanglement would take two such globes, separate them by continents, and yet still ensure that when one settles on a place, the other instantly reflects the complementary result. It is as though the fabric of reality knits them together across space itself. For most of human history, emptiness was seen as nothingness, a void lacking substance. The ancients argued whether a true vacuum could even exist. Yet now we know that what appears empty is anything but. The vacuum is alive with the hum of quantum fields, restless and never still. Out of this seething background, pairs of particles blink into being, borrow energy for the briefest moment, then annihilate back into nothing. This constant agitation, invisible to our senses, creates measurable effects. It shifts the energy levels of atoms and even exerts forces, a whisper from the void itself. The illusion of emptiness hides an ocean of activity that fills the universe. It is within this ocean that the rules of entanglement play out. Particles can be born already entangled, their properties tied together by the mathematics of quantum fields. They may travel apart, but the bond does not fade. To classical minds, this defies explanation. How can two objects remain connected without exchanging signals? How can measurement here decide the outcome there? Yet again and again, experiments confirm the truth. The link does not care about distance. It does not weaken across a laboratory, or across mountains, or across orbit. It is as if space itself does not intrude upon the relationship. This strangeness challenges our language. We are accustomed to speaking of communication, of forces that travel, of causes that lead to effects. But entanglement is not communication in that sense. No signal passes. No information travels faster than light. Instead, the particles share a single description, a wave function that spans them both. They are two aspects of one system, and when one side is measured, the wave function as a whole adjusts. To think of them as independent is to misinterpret the picture. Separation, in the quantum world, is not what it seems. This is why many physicists describe entanglement as the most profound feature of quantum mechanics. It does not merely alter details of measurement. It forces us to rethink what it means for something to be distinct, for something to be here, rather than there. It asks whether the universe is fundamentally composed of individual parts, or whether it is a web of relations where the parts are illusions, born of our perspective. Einstein, Podolsky, and Rosen raised this issue directly in their famous paradox. They believed that if quantum mechanics were complete, it would allow for this instantaneous influence, and that was unacceptable. Therefore, they argued, hidden variables must exist. Something unseen must decide the outcomes in advance, preserving locality and realism. For decades, this question sat unresolved, a puzzle at the heart of physics. The illusion of emptiness had already fallen away, replaced by a restless quantum vacuum, but now the illusion of separation itself was under attack. As we reach the close of this first chapter, we stand where those pioneers once stood, staring at a world that feels like a dream. The ground beneath us is not solid, but woven of fields. The objects around us are not certain, but probabilistic. The space between them is not empty, but alive with hidden energy. And within this theater, particles can be joined across distances in ways that challenge every instinct we carry from the classical world. This is the stage upon which the story of quantum entanglement unfolds. It begins in the early 20th century, when giants of science wrestled with the meaning of these discoveries. It deepens with Einstein's challenge, the paradox that questioned the completeness of physics, and it builds toward experiments that would prove beyond doubt that the universe is stranger and more beautiful than anyone had imagined. The quantum world is our foundation, and within it lies the key to understanding the most mysterious connection in all of science. At its heart, quantum entanglement is the simple yet astonishing idea that two particles can become linked in such a way that they no longer carry separate existences. They may be born together, interact for the briefest instant, and then fly apart in opposite directions. Yet, despite the gulf between them, they remain bound by a shared quantum state. It does not matter how far they travel, whether they are a few centimeters apart on a laboratory table or separated by thousands of kilometers across the Earth. The moment one is measured, the other reveals a perfectly correlated property. This is not the transmission of a signal, nor a trick of timing. It is as though nature itself insists that these particles are two faces of a single coin. To glimpse this strangeness, imagine rolling two dice. In our ordinary world, each die spins independently. You may get a 3 on one and a 5 on the other, or a 6 and a 2. Nothing in the nature of dice rolling forces the results to match. Now imagine instead that no matter how you roll them, the two always land on the same number. A 4 on the left, a 4 on the right, a 1 on the left, a 1 on the right. Even if you separate the dice, carry one across the city, toss them at the same time, the results remain locked together. Such behavior in the classical world would be called impossible. In the quantum world, it is the rule we call entanglement. How does this come to be? The answer lies in the mathematics of the wave function. When two particles interact in certain ways, Their individual wave functions no longer suffice to describe them. Instead, they must be treated as a single combined wave function. That wave function does not break apart simply because the particles move away from one another. It remains whole, spanning both, dictating outcomes as though the pair were one system. When you measure one, you are really collapsing the shared wave function, forcing both particles to reveal results consistent with that common state. Consider a pair of photons born from the same process of emission. Their polarizations are linked. Measure one, and you immediately know the orientation of the other. Consider a pair of electrons with spins coupled in opposite directions. No matter how far apart they drift, measure one, and you instantly know the spin of its partner. This is not guesswork. It is not a hidden signal sent between them. It is the unavoidable result of their entangled wave function. The human mind resists this idea because we are trained to see the world in terms of independent objects. When you place one cup on the table and another on the shelf, you expect them to exist separately. You do not imagine that lifting the cup on the table could instantly decide something about the cup on the shelf. Yet, at the quantum scale, independence is a fragile illusion. Entanglement teaches us that the very building blocks of matter can share existence, even when their locations are far apart. Experiments reveal this truth with clarity. When entangled particles are measured, the results are not random scatterings, but perfectly correlated patterns. One might think of hidden strings connecting them, pulling one result into alignment with the other, but no such strings exist. No mechanism within space carries the message. The correlation arises not from transmission, but from unity. The particles are not two, but one system manifesting in two places. This idea may sound mystical, but it is supported by the most rigorous mathematics and experiments of modern science. Quantum entanglement is not philosophy. It is testable, measurable, repeatable, and already serves as the foundation for emerging technologies. Yet its essence still stirs unease. How can separation be an illusion? How can distance be irrelevant? How can something be shared across space without traveling? These questions lead us deeper into the strangeness of the quantum domain. Entanglement is more than a curiosity. It is the bedrock of quantum theory, a property that forces us to question what it means for objects to be distinct. As we step further into this mystery, we see why even the greatest minds of the 20th century struggled with its implications. They saw that if entanglement were real, the universe itself must be interconnected in ways that defy ordinary causality. And yet, the evidence would grow until denial was no longer possible. Entanglement becomes more vivid when we trace how it differs from the ordinary uncertainties of the classical world. Imagine two envelopes, each sealed with a slip of paper inside. One contains the word yes, the other contains the word no. If you take one envelope to Paris and the other to Tokyo, the moment someone opens one and finds yes, they will instantly know the other holds no. At first, this might sound like entanglement, but it is not. The contents were decided long before the envelopes were opened. Nothing mysterious occurs when the seal is broken. It is simply that knowledge of one reveals knowledge of the other. True entanglement is stranger. In a quantum experiment, the slips of paper inside are not written in advance. Instead, both envelopes remain in a state of uncertainty until one is opened. Only then is the outcome decided. And at that exact instant, the result in the other envelope is fixed as well. The crucial difference is that in entanglement, the results do not exist until the moment of observation. The outcomes are created together by a wave function that binds them. That is what makes entanglement so alien to our intuitions. Physicists describe this mathematically with a combined state. If one electron is spinning up and another is spinning down, the entangled state might be written not as one fixed up and one fixed down, but as a superposition of both possibilities. They are in a blend of up, down, and down, up at the same time. When a measurement occurs, the superposition collapses, and the system chooses one. The instant it does, both particles align to reflect the same choice. What seems like magic is simply the unfolding of the shared state. Imagine a pair of dancers rehearsing. At first, they may move independently, but then the music begins, and their motions become entwined. Each step of one is mirrored in the motion of the other. Even if separated by a curtain, their rhythm stays connected. Entanglement is the subatomic equivalent of this perfect choreography, except that it does not depend on practice or signals. It arises naturally from the rules of quantum mechanics, the inevitable consequence of particles sharing a wave function. Skeptics might wonder if there is some hidden clockwork ticking beneath the surface. Could there be hidden variables that secretly determine the outcomes in advance, waiting to be revealed at measurement? This was the hope of those unwilling to abandon classical notions of locality. But if hidden variables were responsible, the patterns of correlation would obey strict mathematical limits. Later, as we will see, experiments would show those limits broken again and again. The universe refuses to be classical in disguise. Entanglement extends beyond pairs of particles. Entire groups can be linked together, forming complex webs of correlation. In principle, whole systems of many particles can share a single entangled state. Though fragile and easily disturbed by the environment, these states have become tools in laboratories around the world. Scientists entangle photons, atoms, even small molecules, watching as the quantum connections persist until an outside influence breaks the spell. Each demonstration strengthens the evidence that entanglement is not a theoretical dream but a genuine property of the world. One might ask whether this allows faster-than-light communication. Could we send messages instantly across space by manipulating one particle and observing the other? The answer is no, though the reasons are subtle. The results of each measurement are random, and no one can control what outcome appears. The correlations show themselves only when results from both sides are compared. Entanglement, therefore, does not carry usable information faster than light. It does not break relativity. Instead, it reveals that reality itself is non-local in structure, even if communication remains limited by the cosmic speed of light. As unsettling as it is, entanglement has been verified countless times. Polarization measurements of photons, spin tests of electrons, energy correlations of atoms, all converge on the same conclusion. When particles share a wave function, distance becomes irrelevant. Their outcomes are linked in a way no classical picture can explain. Entanglement is not an illusion born of faulty measurement. It is one of the most secure discoveries in all of physics. The deeper consequence is philosophical. If particles cannot be described independently once entangled, what does that say about the universe itself? If the most basic units of reality are connected in ways that transcend space, perhaps the separation we see between objects is only apparent. Perhaps the cosmos is less a collection of parts than a single whole, endlessly expressing itself in correlations. Entanglement whispers that the boundaries we perceive may be illusions cast by limited perception. And so, from simple analogies of dice and envelopes, we arrive at a profound truth. Entanglement is not about spooky magic, nor about messages leaping faster than light. It is about unity, about the refusal of the quantum world to fragment into isolated pieces. This unity persists even as particles drift across great distances, telling us that the foundations of reality are woven together more tightly than we ever imagined. Entanglement first lived as mathematics on paper, fragile symbols that hinted at a reality too strange to accept without doubt. But nature does not bend to human comfort. When scientists tested these ideas, the results made it undeniable. Again and again, entangled particles behaved in ways that no classical picture could reproduce. One of the earliest demonstrations used photons, particles of light, created in pairs. When certain atoms are excited and then release energy, they can emit 2 photons at once. The laws of conservation require that the properties of these photons be connected. Their polarizations, the directions in which their electric fields oscillate, are not independent, but entangled. When one is measured to be aligned in a certain way, the other reveals the complementary orientation. no matter how far apart the detectors are placed. At first, the experiments were simple, performed across a few meters in laboratories. Later, physicists pushed the distances farther, across entire campuses, across cities, eventually across mountains. Always the correlations remained. The photons behaved as though space were irrelevant, their shared state unbroken by separation. Einstein, Podolsky, and Rosen had argued that quantum mechanics must be incomplete. Their paradox suggested that if the theory were correct, then either information traveled faster than light, or reality did not exist independently before measurement. For Einstein, both choices seemed impossible. But experiments showed that quantum mechanics was not incomplete in this way. The correlations matched exactly what the theory predicted, with no sign of hidden variables determining the outcomes. The universe was indeed stranger than Einstein allowed himself to believe. To make sense of this, we must remember the crucial distinction between correlation and communication. When one entangled particle is measured, its partner instantly takes on the corresponding result. But no message has traveled between them. The outcome of each measurement is random, unpredictable, on its own. Only when the two sets of results are later compared does the pattern emerge, revealing that the randomness on each side was in fact synchronized. The speed of light remains unbroken, while the unity of the entangled state persists across the gulf. This does not mean entanglement is useless. On the contrary, it has become the engine of new technologies. In laboratories, researchers now create chains of entangled photons and atoms, building the foundations of quantum computers. These machines use entangled states to perform calculations in ways impossible for classical devices, exploring countless possibilities at once before collapsing into answers. Entanglement also secures communication through quantum cryptography. If a pair of photons is entangled, any attempt to spy on the connection immediately disrupts it, revealing the intrusion. In this way, entanglement offers a method of encryption guaranteed by the laws of physics themselves. But before these applications could be realized, the physics community needed to be convinced that entanglement was real and not a trick of incomplete understanding. This proof would come with a deeper test, one that went beyond simply measuring correlations. It would require a principle that could distinguish between hidden variables and genuine quantum strangeness. That principle was given by John Bell, whose theorem provided a way to test Einstein's doubts. Bell's inequalities drew a line between the predictions of classical hidden variables and those of quantum mechanics, crossed the line, and the conclusion was clear. The world is not classical. The world is entangled. As we close this chapter, the idea of entanglement has grown from a mathematical quirk to an unavoidable feature of reality. Two particles can share a single state, and when one is measured, the other reflects that choice, no matter the distance. The dice roll together, the envelopes are written only at the moment of opening, and the photons whisper the same result across the night sky. Einstein once called this spooky action at a distance, a phrase meant as criticism, but history has transformed it into a badge of wonder. The spookiness is not a flaw in the theory. It is the universe revealing itself, telling us that separation is not what it seems. And now, as we step into the next chapter, we will follow Einstein's objections, his refusal to accept this strangeness, and the paradox he raised with Podolsky and Rosen. It was a challenge that forced physics to sharpen its understanding, and in answering it, we would come closer than ever to uncovering the true nature of reality. In the spring of 1935, three physicists gathered their thoughts into a paper that would echo across generations. Albert Einstein, Boris Podolsky, and Nathan Rosen set out not to deny the successes of quantum mechanics, but to expose what they believed was its incompleteness. The theory worked with uncanny accuracy, predicting atomic spectra, radioactive decay, and the behavior of electrons in metals. Yet Einstein remained unsatisfied. To him, physics was not only about predicting outcomes, It was about describing reality itself, and in his view, the quantum description fell short. The heart of their argument was simple but devastating. If quantum mechanics were complete, then entanglement implied that two particles could be connected in such a way that measuring one instantly decided the state of the other, even if the two were light years apart. Einstein believed that this could not be the full story. Either the particles carried hidden instructions, unknown variables that predetermined the results, or the quantum description was incomplete. He could not accept the idea of instantaneous influence, which seemed to violate the very core of relativity. The speed of light was the universal limit. Nothing, not even information, could travel faster. Einstein had long distrusted the probabilistic nature of quantum theory. He famously declared that God does not play dice with the universe. By this he meant that he could not believe reality was fundamentally random, determined only when observed. For him, probabilities reflected ignorance, not the true nature of things. If you rolled dice in a casino, you might not know the outcome, but the result was already determined by the throw. He believed the same must hold for particles. They might appear uncertain, but beneath the uncertainty, hidden variables would carry the truth. The EPR paper, as it came to be called, sharpened this critique. Imagine, they wrote, two particles that interact and then fly apart. Quantum mechanics describes them as entangled, sharing a single wave function. If you measure one, you instantly know something about the other. For example, if the total momentum of the pair is 0, then measuring the momentum of one immediately tells you the momentum of the other, no matter how far away it has traveled. In classical thinking, this means the second particle must have always possessed that momentum. The measurement simply revealed it, but quantum mechanics insisted otherwise. The measurement created the value at that instant, and somehow, the other particle instantly conformed. To Einstein, this was unacceptable. He called it spookhafte Fernwirkung, spooky action at a distance. The phrase captured his frustration. He could not accept a universe in which space and time lost their role as in forces of cause and effect. Relativity demanded locality. Influences must propagate step by step, never faster than light. If quantum mechanics allowed otherwise, then something was wrong with the theory. Either hidden variables were missing, or the theory was incomplete. Podolsky and Rosen helped formalize the argument, laying it out with mathematical clarity. Their conclusion was cautious, but firm. Quantum mechanics, they wrote, could not be considered a complete description of physical reality. It was a brilliant move, for it placed the burden of proof back on the defenders of quantum theory. If entanglement was real, then physics needed to explain how to reconcile it with relativity. If it was not real, then experiments would one day reveal the hidden variables lurking beneath the probabilities. At the time, many physicists shrugged. Quantum mechanics worked, and its predictions matched experiments with unmatched precision. Why worry about philosophical discomforts? Niels Bohr, Einstein's great debating partner, responded that the EPR paradox misunderstood the nature of quantum measurement. For Bohr, there was no deeper reality beneath the wave function. The wave function was the reality, and questions of hidden variables were misguided. But Einstein was not satisfied with such answers. For him, physics without realism was incomplete. The debates between Einstein and Bohr had begun years earlier, at the Solvay conferences of the 1920s, where the giants of the age gathered to wrestle with the new quantum theory. There, Einstein challenged Bohr with thought experiments, clever setups, designed to reveal contradictions in the uncertainty principle. Again and again, Bohr defended the theory, showing that Einstein's traps were illusions once relativity and quantum rules were combined. Yet even when defeated in detail, Einstein did not relent in spirit. He knew that the theory worked, but he doubted that it told the whole truth. The EPR paper was the culmination of his doubts, the sharpest form of his objection. It would take decades before technology advanced enough to test these ideas. In 1935, entanglement remained a ghostly prediction, unconfirmed by direct experiment. For Einstein, That was enough to treat it as a sign of incompleteness. For others, it was an opportunity, a challenge, waiting to be resolved. Could experiments one day prove or disprove the reality of entanglement? Could they show whether hidden variables existed? At the time, the question remained open, a puzzle lodged at the heart of physics. And so, as the curtain falls on this chapter, we see Einstein not as a skeptic of science, but as its most devoted guardian. He demanded clarity, completeness, and realism, even in the face of a theory that worked. His objection to entanglement was not born of stubbornness, but of conviction that nature must be intelligible, that the universe could not mock our search for truth with randomness and spookiness. Yet history would prove otherwise. In the decades to come, new thinkers and new experiments would test the very questions Einstein posed. They would find answers he would never have accepted, but which the universe insisted were real. Einstein's unease did not fade with time. The more quantum mechanics triumphed in laboratories, the more determined he became to point out its philosophical cracks. To many of his colleagues, this seemed like stubbornness. After all, the new theory explained atomic spectra, radioactive decay, and even the chemical bonds that held life together. It predicted phenomena with uncanny precision. Why insist on hidden variables or deeper layers of reality when the mathematics already matched nature so well? But Einstein believed that predictive success was not enough. A map might lead you to your destination, yet still fail to reveal the landscape's true shape. Quantum mechanics, in his eyes, was such a map. His debates with Niels Bohr embodied this tension. Bohr accepted the strangeness of the quantum world as final. For him, asking what lay beneath the wave function was like asking where the sun goes at night. The wave function was the complete description of nature, and to demand more was meaningless. Einstein resisted this view with every fiber of his being. At the Solvay conferences, he would present thought experiments meant to expose flaws. Could one measure the path of a particle while still observing its interference pattern? Could one trap a photon in a box and weigh it to reveal its energy with certainty, undermining the uncertainty principle? Again and again, Bohr replied, showing that relativity and the rules of quantum mechanics work together to close the loopholes. Einstein's clever scenarios dissolved under Bohr's replies, yet the debates never ended. Each evening after the sessions, the two giants would walk together, arguing into the night. Their disagreements were more than intellectual games. They were clashes of worldviews. Einstein believed in an objective reality that exists whether or not we observe it. Bohr believed that reality cannot be separated from the act of measurement. For Einstein, physics without realism was incomplete. For Bohr, physics without quantum mechanics was unthinkable. Their arguments echoed through the halls of science, shaping generations of physicists who would take sides, some aligning with Bohr's acceptance of the strange, others sympathizing with Einstein's demand for clarity. The EPR paradox sharpened the stakes. It was no longer about philosophical taste. It was about whether physics could claim to be a complete description of nature. If two particles could remain entangled across space, then either information traveled faster than light, violating relativity, or the particles had hidden instructions, predetermined outcomes waiting to be revealed. Einstein leaned toward hidden variables, though he never produced a concrete model. He hoped future generations would uncover the deeper structure he believed must exist. The paradox raised a profound question. What does it mean for something to be real? If we measure one particle and instantly know something about another far away, does that mean the distant particle always possessed that property? Or does reality itself crystallize only at the moment of measurement, spread across both particles until collapsed? For Einstein, the first answer was obvious. For Bohr, the second was unavoidable. In the years that followed, the physics community largely sided with Bohr, not because his interpretation was philosophically satisfying, but because it worked. Quantum mechanics was fertile, explaining phenomena no other theory could touch. Einstein's objections, though respected, seemed increasingly like the protests of a man unwilling to accept the new order. Still, his concerns lingered. Even those who followed Bohr admitted that entanglement was bizarre, unsettling, and not yet experimentally tested in a decisive way. The debates of the 1930s and 40s planted seeds that would only sprout decades later, when experiments finally matured enough to decide the issue. Einstein himself would never live to see the results. In his final years, he continued to pursue a unified field theory, a grand description that would reconcile gravity and electromagnetism, perhaps even absorb quantum mechanics into a deeper whole. He never succeeded. Yet his suspicion that quantum theory was incomplete kept the question of entanglement alive, waiting for someone to find a way to test it. At the time of the EPR paper, the paradox was little more than a philosophical challenge. It was powerful, but intangible. There was no clear method to prove or disprove Einstein's claim. To many physicists, it seemed destined to remain a matter of interpretation. Some called it a ghost story, others an annoyance, a distraction from the real work of applying quantum mechanics. But a few kept the question alive, quietly wondering whether entanglement was more than a mathematical curiosity. Could the universe truly be so strange? Or would hidden variables one day rescue locality and realism? The answer would not arrive until the 1960s, when John Bell, a physicist from Northern Ireland, devised a way to test the very assumptions that Einstein had insisted upon. He would show that the difference between hidden variables and entanglement was not just philosophy. It could be measured. His inequalities would carve a line through the debate, offering an experiment to reveal which vision of reality the universe obeyed. But before Bell's breakthrough, the physics world had to wrestle for decades with the uncomfortable possibility that Einstein's greatest objection might also be his greatest defeat. Einstein's objection, sharpened in the 1930s, became one of the most enduring puzzles of modern science. For the remainder of his life, he returned again and again to the conviction that quantum mechanics was not the last word. He admired its precision, respected its predictive power, but could not accept its vision of reality as complete. To him, the image of two particles separated by great distance, yet locked in an instantaneous embrace, was not only unsatisfying, but impossible. He trusted the universe to be orderly, local, and governed by cause and effect that traveled no faster than light. His colleagues were divided. Some believed that Einstein's resistance was the stubbornness of a man, out of step with a new generation. Others sympathized with his discomfort, sensing that quantum mechanics, though successful, left deep mysteries unresolved. The physics community pushed forward with calculations and experiments, building technologies and discoveries while setting aside the question of whether the foundations were philosophically sound. The practical triumphs were undeniable. Quantum mechanics explained semiconductors, superconductivity, the inner workings of stars. For many, that was enough. Yet in quiet conversations and in the margins of papers, the EPR paradox lingered like a shadow. As the years passed, Einstein grew older, his hair white, his figure bent with time. He continued to work on a unified field theory, hoping to reconcile the forces of nature into a single elegant description. He dreamed of equations that would embrace gravity, electromagnetism, and perhaps more, reducing the complexity of the cosmos to a deeper harmony. But he never succeeded. His papers in his later years were often ignored. The physics world, more focused on nuclear energy, particle accelerators, and the explosive progress of new discoveries. Still, his warning about the incompleteness of quantum mechanics remained in the background, a challenge waiting for resolution. When Einstein died in 1955, the EPR paradox remained unanswered. There were no decisive experiments, no theorems that could settle the question once and for all. Many assumed the paradox would fade into history, an elegant footnote to the rise of quantum mechanics. Yet others saw it differently. They understood that Einstein had identified something profound, a crack in the foundation that could not be ignored forever. That reckoning arrived in the 1960s, when a quiet and brilliant thinker named John Bell asked the question again. Bell wondered whether it was possible to tell, by experiment, if the world obeyed Einstein's vision of hidden variables or Bohr's vision of entanglement. He discovered that it was. By framing inequalities that local hidden variable theories must obey, Bell provided a way to test reality itself. If experiments violated his inequalities, then no hidden variables could save Einstein's dream. The universe would be revealed as non-local, bound by entanglement, as quantum mechanics had always suggested. Bell's theorem transformed the EPR paradox from a philosophical debate into an experimental challenge. It meant that the strange unity Einstein rejected could be tested, measured, confirmed, or denied by data. Physics would no longer be divided by words and arguments. The universe itself would provide the answer. And when the experiments came, they would tip the scales in favor of entanglement, vindicating the very spookiness Einstein had fought against. Thus, the story of Einstein's objection is not one of stubbornness, but of courage. He stood against the tide of his time, unwilling to accept strangeness without question, unwilling to mistake predictive power for completeness. He asked whether quantum mechanics truly described reality or merely predicted appearances. In doing so, he forced the scientific world to sharpen its theories, to test its assumptions, to never rest content with easy answers. Though history would show that the universe is indeed entangled, Einstein's challenge gave us the tools to prove it. His refusal to accept spooky action at a distance ultimately led us to confirm that it was real. And so we arrive at the threshold of Bell's work, the moment when paradox became experiment, when philosophy became physics. The next chapter reveals how inequalities drawn on paper became the decisive test of nature, how laboratories around the world revealed a truth stranger than Einstein could bear. The universe is not local. The universe is entangled. In 1964, nearly 3 decades after Einstein, Podolsky, and Rosen had declared quantum mechanics incomplete, a quiet revolution began. John Bell, a physicist from Northern Ireland, revisited the paradox with fresh eyes. He had long been fascinated by the deep puzzles that others dismissed as philosophy, where many saw only metaphysical debate. Bell saw an opportunity for clarity. He asked whether there might be a way to distinguish, with hard numbers, between the world Einstein imagined and the world described by quantum mechanics. Could mathematics draw a boundary that no hidden variable theory could cross? The brilliance of Bell's insight was its simplicity. He realized that if hidden variables truly existed, then the outcomes of entangled measurements must obey certain statistical patterns. These patterns could be expressed as inequalities, mathematical limits that classical physics could never violate. On the other hand, if quantum mechanics were correct, then in certain experiments, the correlations of entangled particles would break those inequalities. By measuring carefully, one could see which vision of reality the universe followed. To appreciate this breakthrough, imagine again the 2 dice that always land on matching numbers. Einstein might argue that each die carries hidden instructions, predetermined outcomes waiting to be revealed when rolled. Bell asked, if that were true, what patterns of numbers should appear over many rolls? He showed that those patterns would never exceed certain limits. But the predictions of quantum mechanics went beyond those limits. Thus, if experiments revealed correlations stronger than the inequalities allowed, hidden variables could not explain them. This was the genius of Bell's theorem. It took the EPR paradox out of the realm of interpretation and into the realm of experiment. It said, in effect, let the universe decide. By performing tests on entangled particles, one could determine whether locality and realism held, or whether quantum entanglement truly defied them. No longer would physicists need to argue in the corridors of conferences. The laboratory would provide the answer. Bell's paper was dense but revolutionary. It laid out inequalities that any local hidden variable theory must respect. If detectors measuring the properties of entangled particles produced results within those limits, Einstein's hope would be vindicated. If the results went beyond them, the universe would side with Bohr and the quantum view. The theorem was not merely theoretical elegance. It was a challenge to experimenters everywhere. At first, the impact was quiet. The physics world was busy with particle accelerators, nuclear physics, and the dawn of space exploration. Entanglement still seemed like an exotic curiosity. But a few visionary scientists recognized the importance of Bell's work. They understood that it provided the first concrete way to test the strange unity at the heart of quantum mechanics. Slowly, laboratories began to design experiments to put Bell's inequalities to the test. The early experiments were rough, plagued by technical limits. Detectors were inefficient, sources of entangled particles unreliable. Yet even with these imperfections, results hinted that the universe leaned toward quantum mechanics. The correlations exceeded the limits classical hidden variables would allow. The data suggested that Einstein's dream of local realism could not be preserved. In time, more refined tests would come. Photons, emitted from carefully prepared crystals, measured by detectors placed kilometers apart, revealed violations of Bell's inequalities with clarity. The entangled particles behaved exactly as quantum mechanics predicted, their correlations stronger than any classical picture could explain. Hidden variables, if they existed at all, could not be local. The universe was revealing itself as fundamentally non-local, its parts connected in ways Einstein would never accept. Bell himself remained modest. He knew that his theorem did not answer every philosophical question, but it provided a bridge from paradox to data, from speculation to measurement. It gave physics the power to decide, not by opinion, but by experiment. And the experiments were clear. The inequalities were broken. Entanglement was real. As the story of Bell's theorem unfolded, the physics community began to see entanglement not as a curiosity, but as a defining feature of reality. The ghostly predictions of quantum mechanics had passed their most decisive test. The universe had declared itself entangled, non-local, and stranger than classical physics ever imagined. And yet, the implications were only beginning. If entanglement was real, then it was not just a puzzle of foundations. It was a resource, something that could be harnessed for technology, for communication, for computing. The very feature that Einstein dismissed as spooky action at a distance would one day become the engine of 21st century innovation. The first serious attempts to test Bell's ideas began in the late 1960s. Experimental physics was advancing, detectors improving, and sources of entangled photons becoming more accessible. Still, the challenge was immense. To show violations of Bell's inequalities, scientists needed particles that could be entangled reliably and measured with precision, while ensuring that no ordinary signal could sneak between the detectors. If results were sloppy, skeptics could always argue that hidden variables were not disproved, only hidden behind technical flaws. One of the earliest efforts came from American physicist Stuart Friedman and John Clauser in 1972. They set up a source of entangled photons and placed detectors to measure their polarizations. Over many trials, they collected data to compare against Bell's limits. Their results suggested a violation of the inequalities, leaning toward the predictions of quantum mechanics. It was a bold first step, but the technology of the time left loopholes. Detector efficiency was low, meaning many particles were missed. Critics argued that perhaps the particles that were detected were biased, skewing the results. The debate remained unsettled, though the evidence began to tip away from Einstein's hopes. Throughout the 1970s, further experiments pressed forward. At universities across the world, physicists refined their photon sources and detectors. The results kept nudging in the same direction. Violations of Bell's inequalities, correlations too strong for any local hidden variable theory to explain. But the doubts lingered. Could the particles somehow exchange information at subliminal speeds within the experimental time windows? Could flaws in detector design create illusions of quantum strangeness? It was in the early 1980s, in a laboratory just outside Paris, that the decisive breakthroughs occurred. A young French physicist named Alain Aspect and his team at the Institut d'Optique designed experiments of unprecedented ingenuity. They not only produced entangled photons, but also switched the settings of their detectors rapidly while the photons were already in flight. This ensured that no signal, even one traveling at light speed, could coordinate the outcomes in time. The detectors made their choices of measurement orientation while the photons were crossing the distance between them. In such a setup, no hidden influence could arrange the results without exceeding the speed of light. The outcome was stunning. The data showed clear and undeniable violations of Bell's inequalities. The correlations matched exactly what quantum mechanics predicted, stronger than any classical hidden variables could account for. Einstein's vision of local realism crumbled under the weight of experimental proof. Nature itself had spoken, and it declared entanglement real. Aspect's experiments were celebrated as the turning point. For decades, the debate had hovered in the realm of philosophy, a clash of giants between Einstein and Bohr. Now the laboratory had provided the verdict. Entanglement was not a ghost story. It was the way the universe worked. What had once been dismissed as spooky action at a distance was now the cornerstone of a new understanding of reality. The results inspired generations of physicists. Researchers across Europe, America, and Asia repeated and refined the experiments. They closed loopholes, increased detector efficiencies, extended distances. Each new test confirmed the same truth. Bell's inequalities were broken. The classical vision of locality could not survive, and entanglement was here to stay. Yet with triumph came deeper questions. If particles can remain connected across space, what does that say about the nature of reality itself? If measurement here can dictate correlations there, what becomes of the notion of separateness? These were not just puzzles for philosophers. They were questions for physicists, for engineers, for anyone who hoped to use entanglement in the emerging fields of quantum communication and quantum computing. Bell had opened the door, Aspect had walked through it, and the scientific world followed. The EPR paradox was no longer an unresolved challenge. It was history. The universe had chosen its side, and it had chosen strangeness. The years after Alain Aspect's landmark work saw an explosion of creativity. Laboratories across the globe took up the challenge of pushing Bell's theorem further, testing entanglement under ever more demanding conditions. Each new experiment refined the precision, addressed loopholes, and added confidence to the conclusion that quantum mechanics was right, Einstein's hidden variables were wrong, and the universe was more deeply connected than anyone had imagined. One concern had been the detection loophole. Early experiments missed too many particles. If detectors only captured a fraction of the entangled pairs, skeptics could argue that perhaps the ones that were detected were a biased sample, already predisposed to violate Bell's inequalities. To answer this, physicists built better detectors, capturing more and more of the photons or ions in play. With higher efficiency, the data became harder to dispute. Another issue was the locality loophole. Could the detectors, in some subtle way, coordinate with each other within the time it took the photons to travel? Aspect's rapid switching went a long way to closing this, but experiments in the decades that followed pushed it further. Detectors were placed kilometers apart, their settings switched by random processes, sometimes even influenced by cosmic events like distant starlight, to guarantee unpredictability. Each step tightened the net, ensuring that no classical influence could explain the results. By the early 21st century, so-called loophole-free tests finally appeared. These experiments combined high-efficiency detectors with space-like separation of events, closing both major loopholes at once. The results were unambiguous. Quantum correlations exceeded Bell's inequalities just as predicted, with no escape routes left for local hidden variable theories. The verdict was final. Entanglement was not only real, it was unavoidable. The universe is non-local in structure, even though no usable information passes faster than light. Bell himself did not live to see the full flowering of his work. He died in 1990, before Aspect's legacy reached its culmination. Yet his theorem remains one of the most important contributions in all of physics, transforming a philosophical paradox into an experimental cornerstone. His insight reshaped our understanding of reality, providing clarity where even Einstein had doubted. For the physics community, the implications were profound. No longer was entanglement a curiosity hidden in equations. It was a proven, measurable, repeatable phenomenon. This shifted entanglement from a battleground of interpretation to a foundation for new possibilities. Physicists began to see it not only as evidence of quantum strangeness, but as a resource to be harnessed. If nature offers particles bound across space, then perhaps humans could use that bond to compute in ways classical machines cannot, to communicate with unbreakable security, to teleport quantum information from one place to another. What Einstein dismissed as spooky action at a distance began to look like the engine of future technology. And so, as the 20th century gave way to the 21st, the story of Bell's theorem evolved. It was no longer simply the resolution of a paradox. It was the opening of a new frontier. Entanglement, tested and proven beyond doubt, became the key to the next generation of physics and engineering. The experiments that shattered Einstein's objection did more than settle a debate. They revealed a universe richer and stranger than we dared to hope. They showed us that separation is not absolute, that distance is not the barrier we thought it was, and that reality itself may be woven from threads of connection invisible to our eyes. And with this new certainty, we step forward into the next stage of the story. The laboratory proofs of entanglement became the seeds of technology. What once seemed like a ghostly curiosity is now the foundation of quantum computing, quantum cryptography, and quantum teleportation. In the chapters ahead, we explore not only how entanglement shapes our understanding of reality, but how it is reshaping the world of human invention. The story of entanglement begins with paradox and philosophy, but it does not end there. What was once only a riddle for theorists and a test for experimentalists has grown into a practical tool, something that engineers and computer scientists now reach for as they design the next generation of technology. The strangeness that unsettled Einstein has become the raw material of invention. The same quantum links that seemed impossible now form the backbone of new machines, new networks, and new visions of the future. Consider the idea of computing. In the classical world, every calculation is performed by bits, units of information that can take the value 0 or 1. Strings of bits form numbers, letters, images, and instructions. For decades, shrinking transistors on silicon chips made classical computers faster and faster, until billions of operations could be performed in the blink of an eye. Yet no matter how powerful these machines become, they remain bound by the binary choices of their bits. Each bit must be 0 or 1 at any given time. Enter the quantum computer. In this new device, the basic unit is not a bit but a qubit, a quantum system that can exist in a superposition of 0 and 1 at the same time. Entanglement allows qubits to share information across the entire machine, weaving their states together into patterns that cannot be described classically. Where a classical computer explores one possible solution at a time, a quantum computer explores many simultaneously, collapsing into the answer when measured. Problems that would take classical machines longer than the age of the universe may one day yield to quantum machines working with entangled qubits. This is not fantasy. In laboratories today, physicists entangle photons, trapped ions, and superconducting circuits, using them as qubits. Though fragile and prone to errors from environmental noise, these qubits have already been used to demonstrate calculations impossible for classical machines of similar size. Google's quantum processor Sycamore in 2019 performed a task in minutes that would have taken the best supercomputers thousands of years. Though the result was specialized and not directly useful, it proved that entangled qubits can offer power beyond classical reach. Entanglement does not only fuel computing, it also secures communication. Classical encryption relies on mathematical difficulty, on problems like factoring large numbers that are hard for ordinary computers to solve. But in principle, clever algorithms or future machines might crack these codes. Quantum cryptography, by contrast, uses the laws of physics themselves. Two parties can share entangled photons as cryptographic keys. Any attempt to eavesdrop disturbs the entanglement, revealing the intrusion immediately. This makes the communication unbreakable, not by human ingenuity, but by the fundamental rules of the quantum world. Perhaps the most dramatic application is quantum teleportation. Here, entanglement is used to transfer the state of a particle from one location to another without moving the particle itself. The process does not send matter through space. Instead, it uses entanglement to recreate the exact quantum state at a distant location, while the original is destroyed. In this way, information is transmitted securely and perfectly, without ever existing in a vulnerable form along the path. Teleportation has already been demonstrated with photons across city networks and even from the ground to orbiting satellites. What once belonged to science fiction now exists in physics laboratories. Each of these applications rests on the same foundation. Entanglement, once dismissed as spooky, is a real and usable property of nature. By weaving particles together across distance, it provides power and security that classical systems cannot match. The dice that always land the same, the envelopes written only at the moment of opening, are no longer just metaphors. They are technologies in action, reshaping the world we live in. The implications extend far beyond faster computers or safer communication. They touch the very way we understand information itself. In the classical world, information is an abstract construct, written on paper or stored in silicon. In the quantum world, information is physical, inseparable from the particles that carry it. Entanglement shows that information can be shared across space, that it can be distributed without being copied, and that it can be protected by the very laws of reality. This insight may be as revolutionary as the discovery of electricity, opening doors we have only begun to glimpse. And as engineers refine these technologies, the dream of a quantum internet comes into view, a network of entangled nodes spanning the globe. Such a system could link computers, satellites, and laboratories with absolute security, transmitting quantum states instantly across continents. It would not replace the classical internet, but extend it, adding a layer of connectivity that rests on the deepest truths of physics. But before such a future can arrive, entanglement must be mastered on ever larger scales. Fragile as soap bubbles, entangled states collapse easily under the touch of the environment. Heat, vibration, stray electromagnetic noise, all conspire to break the delicate quantum links. To build practical machines, scientists must learn to protect and correct these states, to stabilize them against the chaos of the wider world. The story of entanglement today is not just one of triumph, but of challenge, a race to tame the strangeness for human use. Even so, progress is rapid. From the first entangled photons in laboratories to entangled networks spanning cities, from primitive qubits to machines with dozens or even hundreds of them, the march is steady. Each new breakthrough confirms the same truth. What Einstein dismissed as spooky action is in fact the key to a technological revolution. The promise of quantum cryptography has already stepped beyond the laboratory and into the real world. In the late 1990s, the first experiments sent entangled photons through optical fibers across short distances. By the early 2000s, networks in cities like Geneva and Beijing demonstrated secure communication over tens of kilometers. Today, some of the largest trials stretch across hundreds of kilometers of fiber, weaving through urban landscapes where classical encryption is vulnerable to attack, but quantum keys remain unbroken. The principle is simple, but profound. Two users, often called Alice and Bob, share entangled photons distributed by a central source. By measuring their photons in randomly chosen orientations, they generate correlated strings of bits. These strings become cryptographic keys. If no one interferes, the correlations remain perfect. But if an eavesdropper, sometimes called Eve, attempts to measure the photons, the entanglement is disturbed, and the discrepancies immediately reveal the intrusion. No clever code breaking is needed. The laws of quantum mechanics themselves guarantee the security. This makes quantum key distribution unique. It does not depend on the hardness of mathematical problems. It does not rely on the assumption that certain algorithms are too difficult for computers to solve. It relies only on the certainty that entanglement cannot be copied without being disturbed. In a world where classical encryption may be threatened by the rise of quantum computers themselves, quantum cryptography offers a solution immune to such dangers. Even more dramatic is quantum teleportation. First demonstrated in 1997, it showed that the quantum state of a photon could be transferred from one place to another using entanglement and a small amount of classical communication. The process destroys the original state and recreates it perfectly at the destination. This does not mean that matter itself is transported through space, as in science fiction. Instead, the delicate information that defines the quantum system is reconstructed elsewhere. The significance is enormous. It means that entanglement can transmit information with absolute fidelity, a tool for building future quantum networks. Experiments have steadily extended the reach of teleportation, from laboratory benches to optical fibers spanning cities, from mountaintops to satellites in orbit. The distances grow year by year. In 2017, Chinese scientists used the Mischius satellite to perform quantum teleportation between ground stations separated by more than 1,000 kilometers. The demonstration showed that entanglement could be distributed not just across laboratories or cities, but across continents, a foundation for a truly global quantum internet. The vision of a quantum internet is compelling. Imagine a world where quantum computers in different cities are linked by entanglement, sharing information with absolute security. Imagine satellites distributing entangled photons across oceans, allowing banks, governments, and individuals to communicate without fear of interception. Such a network would not replace the classical internet, but would complement it, adding layers of security and functionality grounded in the most fundamental laws of physics. To reach this goal, scientists must solve formidable challenges. Entanglement is fragile, easily destroyed by loss in fibers or interference from the environment. Unlike classical signals, entangled states cannot be copied or amplified. If a photon is lost, its quantum state vanishes forever. The solution lies in quantum repeaters, devices that use entanglement swapping and error correction to extend quantum links across long distances. These repeaters are still in development, but progress is steady. Step by step, the dream of global entanglement moves closer. What makes this progress extraordinary is how recent it islanded. Barely a generation ago, entanglement was regarded as little more than a philosophical curiosity. Few imagined that it could one day form the basis of networks, computers, and communication systems. Now, entire fields of research are devoted to taming and applying it. Universities, national laboratories, and private companies invest heavily, racing to unlock the power of entangled states. The transition from paradox to practice is one of the most dramatic in the history of science. And with each success, entanglement becomes more than a curiosity. It becomes infrastructure. Just as electricity once moved from an invisible force to the lifeblood of civilization, so entanglement is moving from the blackboards of theorists to the cables and satellites of engineers. It promises not only faster machines and safer communication, but also a new way of thinking about information itself, as something physical, inseparable from the particles that carry it, and capable of being shared across the very fabric of space. The journey is far from over. The fragility of entangled states still limits the scale of what can be built, but the steady march of progress suggests that what seems delicate today may become robust tomorrow. Just as transistors once seemed too unreliable to replace vacuum tubes, entangled networks today seem fragile. Yet history teaches that persistence and ingenuity can transform fragility into power. The quantum age is young, and its potential is vast. The three great applications of entanglement computing, cryptography, and teleportation are not isolated curiosities. They are threads of a larger story, a story in which quantum mechanics does not merely explain the world but reshapes it. Each application reveals a different face of the same phenomenon. Entanglement is not just a puzzle about how particles behave. It is a resource, as real and as useful as electricity, waiting to be harvested by human ingenuity. Quantum computing shows the raw power of entanglement. Classical bits are like switches, rigidly locked into 0 or 1. Qubits, woven together by entanglement, form a fabric of possibilities that classical machines cannot rival. In small systems, this power has already been glimpsed. Algorithms that search databases, factor large numbers, or simulate molecules run with a speed that hints at a new era. If the challenges of stability and error correction can be mastered, quantum computers may transform industries from medicine to finance, designing new drugs, optimizing global systems, and solving equations too vast for classical machines to attempt. Quantum cryptography shows the security of entanglement. In a world where digital communication is vulnerable to attack, where code breakers and computers grow ever more powerful, the promise of absolute protection is priceless. Entangled photons cannot be copied, cannot be intercepted without betraying the intrusion. This makes them the guardians of information in a way no classical system can match. Already, companies and governments invest in networks that use entanglement to safeguard secrets. In the future, entire economies may rest upon the unbreakable walls of quantum cryptography. Quantum teleportation shows the reach of entanglement. It demonstrates that information can leap from one place to another without crossing the space in between, carried by the unity of entangled states. Though it does not transport matter, it transports something just as valuable: the delicate quantum information that defines the state of a particle. From the laboratory to the skies, from mountaintops to orbiting satellites, teleportation has proven that entanglement is not limited by distance. This opens the door to a quantum internet, a network that binds together computers, satellites, and individuals across the planet with perfect fidelity. Together, these technologies reveal a vision of the future shaped by entanglement. A future where computers solve problems once thought impossible, where communication is absolutely secure, where networks span the globe not only with classical signals, but with the deep connections of quantum states. It is a vision where the spooky action Einstein once rejected becomes as familiar as the hum of electricity in our homes. Yet the path forward is not simple. Entanglement is fragile, undone by the slightest disturbance. Building machines that can control it requires extraordinary precision and ingenuity. Researchers must cool systems to near absolute zero, isolate them from noise, and develop error correction methods that preserve delicate states. The work is painstaking, but progress is relentless. Each year brings new records, new demonstrations, new hints that the barriers are not insurmountable. The significance of this transformation cannot be overstated. Just as the mastery of fire, electricity, and the atom reshaped civilization, so too will the mastery of entanglement. It is not merely a tool for scientists. It is a new layer of reality made available to human use, a doorway into possibilities we have only begun to imagine. And beyond the laboratories, beyond the networks and machines, lies the deeper wonder. Entanglement reminds us that the universe is not built of isolated parts, but of connections. It tells us that separation is not absolute, that distance does not erase unity. By harnessing this truth, we not only build new technologies, but also glimpse the hidden fabric of reality. As we close this chapter, we stand at a turning point. Entanglement has moved from paradox to proof, from proof to practice, and from practice to promise. It is no longer only the subject of philosophical debate or experimental demonstration. It is becoming the foundation of a new technological age. And in the next chapter, we will see how entanglement stretches across space itself, tested not only in laboratories, but across mountains, cities, and even between Earth and orbiting satellites. What was once thought confined to the microscopic realm now reveals itself on cosmic scales, a connection that challenges our very notions of space and distance. At first, entanglement seemed confined to the invisible world of atoms and photons, delicate effects glimpsed only in carefully shielded laboratories. But nature had other lessons to teach. If entanglement was real, then it could not be limited by distance. It must persist, no matter how far the particles traveled. The challenge was to prove it, to take the fragile quantum link and stretch it across kilometers, then across cities, and finally, into the sky itself. What began as a curiosity of the microscopic world has now become a demonstration written across landscapes and even the heavens. The first attempts to push entanglement beyond the walls of a laboratory came in the 1970s and 80s, when detectors grew sensitive enough to capture photons traveling down long optical fibers. Researchers placed entangled photon sources at one end of the fiber and detectors at the other, separated by hundreds of meters. Even with losses in the fiber, the correlations remained. The photons still behaved as if they were two halves of a single system. The message was clear. Entanglement did not fade with distance. It did not unravel, simply because space lay between the partners. By the 1990s, physicists were sending entangled photons through fibers that wound across university campuses, measuring correlations at detectors in separate buildings. The results showed the same strange unity Einstein had doubted, now playing out across city blocks. Each time the experiment scaled upward, entanglement held firm, as if space itself had no power to break the connection. The real breakthrough came when scientists moved beyond fibers and into free space. In 1997, Austrian physicist Anton Zeilinger and his team demonstrated that entangled photons could be sent across 600 meters of open air in Vienna. The experiment used telescopes to send and receive the photons, proving that entanglement could survive not only the confinement of fiber, but also the turbulence of the atmosphere. This was a crucial step, for it suggested that entanglement might one day be tested across vast distances, even from Earth to space. As the experiments grew bolder, the distances stretched further. In 2003, Zeilinger's group extended the range to over 10 kilometers between two mountaintops in the Canary Islands. Later, they increased it to 144 kilometers, sending entangled photons between the islands of La Palma and Tenerife. Across the open ocean, through the shifting air, the photons still arrived entangled, their correlations undisturbed. What had once seemed an impossibility now shimmered across the night sky. These demonstrations laid the foundation for a new era. If entanglement could survive across mountains and oceans, why not to satellites orbiting above the Earth? Why not across continents? The dream of testing entanglement on a planetary scale began to take shape. The same experiments that confirmed quantum theory in the laboratory could now be carried into the heavens, pushing the boundaries of distance and proving that the strange unity of the quantum world was not confined to the microscopic but stretched across the planet itself. Each step forward brought not only confirmation of entanglement, but also inspiration for technology. The same telescopes and detectors that captured photons across mountain ranges hinted at the possibility of quantum communication on a global scale. Secure channels, quantum teleportation, and entangled networks no longer belonged to theory alone. They became goals for engineers and physicists working side by side, building instruments capable of carrying entanglement farther and farther. The story of entanglement across space is still being written, but its first chapters already reveal a universe where distance is powerless against unity. Particles born together can remain together, no matter how far they drift. no matter what lies between them. It is a lesson that defies common sense, but obeys the deepest laws of reality. And as humanity learns to harness it, we find ourselves standing not only in laboratories, but beneath the open sky, watching photons carry their strange bond across the Earth and beyond. The leap from mountaintops to orbit marked a turning point in the history of entanglement. If photons could carry their fragile quantum bonds across 144 kilometers of turbulent atmosphere, then perhaps they could cross the hundreds of kilometers that separate Earth from satellites. This idea, once dismissed as impossible, became the goal of a new generation of physicists who dreamed of testing entanglement on a planetary scale. China led the way. In 2016, the Chinese Academy of Sciences launched a satellite named Meitius, after the ancient philosopher who had written of optics and light more than 2,000 years earlier. This satellite carried an entangled photon source into orbit, as well as telescopes and detectors capable of sending and receiving quantum signals. From its vantage point hundreds of kilometers above the Earth, Meitius became the first laboratory in the sky dedicated to testing quantum entanglement beyond the limits of ground experiments. The results were extraordinary. In 2017, the Meitius team announced that they had successfully distributed entangled photons between ground stations, separated by more than 1,200 kilometers. Photons created aboard the satellite were sent simultaneously to two cities far apart. Yet their correlations remained as perfect as if they had traveled only meters. This shattered previous records and proved beyond doubt that entanglement could be preserved across continental distances. The experiments did not stop there. Meitius was also used to perform quantum teleportation, sending the quantum state of a photon from a ground station up to the satellite. The state was destroyed at the source and recreated perfectly in orbit, demonstrating teleportation across 500 kilometers. For the first time, the delicate information encoded in quantum systems had leapt from the Earth to space. Perhaps most impressively, Meitius enabled quantum key distribution between distant cities. Entangled photons were used to establish secure cryptographic keys between Beijing and Vienna, separated by thousands of kilometers. The keys were unbreakable, guaranteed by the laws of quantum mechanics themselves. This was more than a scientific milestone. It was the first demonstration of a global quantum network, a glimpse of the future quantum internet linking continents with absolute security. These achievements showed that entanglement was not confined to the laboratory or even to regional experiments on the ground. It could be stretched across the world, distributed from orbit, and harnessed for real communication. The spooky action that Einstein doubted now danced between Earth and space, confirmed by detectors on mountaintops and by telescopes pointing at the night sky. Other nations soon joined the effort. Europe and the United States began developing their own quantum satellites. Plans emerged for constellations of orbiting platforms, each distributing entanglement across the globe. The vision was clear. Just as the classical internet spread in the late 20th century, the quantum internet would spread in the 21st, carried not by cables alone, but by satellites, beaming entangled photons across oceans and continents. These milestones did more than prove that entanglement survives over distance. They also silenced one of the last doubts about quantum mechanics. If entanglement could persist across thousands of kilometers of atmosphere and through the challenges of space, then it was not a laboratory trick. It was a fundamental feature of reality. The universe itself seemed to insist that distance did not matter, that particles could share a state, no matter how far apart they traveled. Yet even this is only the beginning. Experiments are now planned to test entanglement across even greater scales, using satellites to distribute entangled photons between continents on opposite sides of the planet. Some scientists dream of cosmic tests, where photons emitted by stars billions of light years apart are used to choose detector settings, ensuring that no hidden variables from our own history could influence the results. In such tests, the universe itself becomes the laboratory, and starlight serves as the random hand that guides the experiment. Entanglement across space is not only a triumph of physics, but a revelation about the nature of reality. It shows that the bonds of the quantum world are not fragile curiosities confined to atoms. They are robust connections that persist across the very scale of the earth and sky. The lesson is as humbling as it is inspiring. Space may divide us, but the quantum world unites. The drive to test entanglement at ever greater scales eventually turned from satellites to the cosmos itself. If particles can remain entangled across thousands of kilometers on Earth and orbit, then perhaps they can remain linked across the universe. Such questions stretch the imagination, but physicists have devised experiments to probe them, using the stars themselves as tools. One of the challenges in Bell tests is choosing measurement settings in a way that guarantees true randomness. If the choices were influenced, even subtly, by hidden variables, then the results might be biased. To close this loophole, researchers turned their eyes to the sky. In 2017, a team used photons from distant stars to decide detector settings in a Bell test. Light emitted hundreds of years ago, long before the experiment, determined the orientations of the detectors. The results again showed violations of Bell's inequalities, confirming entanglement while pushing the possibility of hidden variables further into the past. Other experiments went even farther. By 2019, scientists used light from quasars, galaxies with brilliant cores powered by supermassive black holes, to choose measurement settings. These photons had traveled billions of years before reaching Earth. If hidden variables were to explain the results, they would have had to be set at the birth of the universe itself. Yet the outcomes still showed entanglement, as strong and undeniable as in any laboratory experiment. The conclusion grew inescapable. Entanglement is not a trick of timing, not an illusion of incomplete data. It is woven into the fabric of reality, stretching across cosmic scales. The beauty of these cosmic Bell tests is that they remind us of the unity of science. The same starlight that astronomers study for clues about galaxies can also serve as the random hand that closes loopholes in quantum physics. The universe itself becomes a participant in the experiment, lending its ancient light to confirm the strangest prediction of modern science. This progression, from tabletop tests to mountaintops, from satellites to quasars, reveals a truth both profound and humbling. Entanglement does not weaken with distance. It does not dissolve in the void of space or fade with the passage of time. It persists, as though the universe refuses to let separation define it. In the laboratory, in the atmosphere, in orbit, and across cosmic distances, the message is the same. Particles born together remain together, no matter how far they travel. For technology, this is a gift. If entanglement can be distributed globally, and perhaps even across interplanetary distances, then humanity gains a tool for communication and computation that transcends classical limits. But for philosophy, the lesson is deeper. Entanglement forces us to rethink what space and time mean. If distance cannot undo quantum unity, then perhaps separation itself is not as fundamental as we once believed. As this chapter closes, the stage is set for the next question. If entanglement links particles instantly across space, does that mean it breaks the ultimate speed limit of the universe, the speed of light? Can spooky action at a distance be reconciled with Einstein's relativity? Or must we admit that our deepest theories stand in contradiction? In the next chapter, we explore this apparent clash between entanglement and the cosmic speed limit, and discover why the truth is subtler than it first appears. From the moment physicists first realized that entangled particles reflect each other's states instantly across space, one question has lingered like a shadow. If the connection is immediate, does it mean that something has traveled faster than light? Does entanglement break the most sacred law of relativity, the cosmic speed limit that Einstein himself had defended so fiercely? The question is natural, for the correlations appear instantaneous. Measure one particle here, and the other seems to respond there, no matter how far away. It feels like communication, faster than light, a whisper across the void with no delay. Yet, appearances can mislead. To understand why entanglement does not truly violate relativity, we must look closely at what is happening when two particles share a quantum state. Consider again the example of entangled photons. Their polarizations are linked so that if one is measured as vertical, the other must be horizontal, and vice versa. When the first photon is measured, the outcome seems to determine the second instantly, even across kilometers or more. But the crucial point is this: the result of each measurement is random. No one can control whether the photon comes out vertical or horizontal. The instant correlation is real, but it carries no usable signal. Imagine two friends agreeing in advance to flip identical coins, each hidden under a cup. When they reveal their coins, the results always match both heads or both tails. To an outside observer, this might seem like communication. But if neither friend can control the coin's outcome, then no message has passed. The matching is correlation, not communication. Entanglement is the same, except that unlike coins, the outcomes are not determined beforehand. They are created at the moment of measurement, woven together by the shared quantum state. This distinction between connection and communication is the heart of the matter. Relativity forbids signals or information from traveling faster than light. Entanglement does not break this rule, because no information is carried by the instant correlations. To use them, the results from both sides must later be compared through ordinary channels, which are limited by the speed of light. The entanglement alone cannot transmit a message. It can only reveal the unity of the quantum state when the data are brought together. Still, the situation feels unsettling. How can two particles agree on outcomes instantly without sending a signal? The answer lies in how quantum mechanics describes them. They are not two separate objects with independent states. They are a single system, described by one wave function that spans both. When one side is measured, it is not sending information to the other. It is simply collapsing the shared wave function. The unity existed all along. The separation was an illusion imposed by our classical way of thinking. Einstein found this unsatisfying. He believed that the insistence on randomness meant that the theory was incomplete, that hidden variables must secretly determine the outcomes. But Bell's theorem and the experiments that followed showed that no local hidden variables could explain the correlations. The universe itself is non-local, not in the sense of sending faster than light signals, but in the sense of binding distant parts into one inseparable whole. The beauty of this realization is that it preserves both relativity and quantum mechanics. No signal outruns light. No message is transmitted instantly. Yet the correlations still defy classical explanation. The speed of light remains the limit of communication, while entanglement shows that reality itself is not limited in the same way. It is as though the universe has two layers, one where information travels step by step through space, and another where the underlying connections transcend distance. This duality is not just a curiosity, it is what allows entanglement to be used safely for quantum communication and quantum computing without breaking the laws of relativity. The universe plays fair. It does not let us cheat the speed limit, but it does let us glimpse a deeper order, one in which separation is less absolute than we once believed. And so the paradox dissolves. Entanglement does not break the speed of light. It reveals that speed is not the only measure of connection. Space and time govern communication, but entanglement belongs to a deeper layer where unity is built into the very fabric of reality. It is not faster than light. It is outside the very idea of speed. The temptation to see entanglement as a hidden telegraph, running faster than light, has never fully faded. Again and again, physicists and engineers have asked if the instantaneous correlations could be harnessed to send messages beyond the reach of classical limits. Imagine, they say, an astronaut on Mars and a partner on Earth. If the two share entangled particles, could the astronaut flip one switch and instantly deliver a message home? If such a method worked, communication across the solar system would be immediate, no longer bound by the long minutes it takes for light to cross the gulf between planets. But every attempt to design such a system has failed, and for good reason. The outcomes of entangled measurements are random. The astronaut cannot choose the result of their measurement. They cannot decide that their particle should be spin up to signal yes or spin down to signal no. They can only measure, and the universe delivers a random outcome, though always correlated with the partner's measurement. Without control over the result, no information can be encoded. The only way to reveal the correlation is for the two sides to later compare notes, and that comparison must travel at or below the speed of light. This point is subtle but crucial. Entanglement offers connection, not control. It ties outcomes together, but does not allow one observer to dictate the outcome for another. It is like two dice that always land the same, yet no one rolling them can decide whether the result will be a 3 or a 5. The matching is remarkable, but it cannot carry a message. Relativity remains unbroken. Some physicists have explored whether hidden variables could restore the possibility of control, but Bell's theorem closed that door. Local hidden variables cannot account for the strength of entanglement correlations. Non-local hidden variables, such as those in David Bohm's interpretation, preserve the appearance of control, but do not enable faster-than-light communication either. The no-signaling theorem, a formal result of quantum mechanics, proves that entanglement cannot be used to send information outside the bounds of relativity. The universe guards its speed limit carefully. What then is happening in these instantaneous correlations? The answer lies in how we think about measurement. When we treat two entangled particles as independent objects, the instant matching feels like one must influence the other. But when we treat them as a single system, with one wave function, the mystery softens. The system does not stretch across space in the classical sense. It simply exists as one entity described by one mathematical object. Measuring one part collapses the whole. No signal passes between them, for there are not truly two separate things to begin with. This perspective reframes the paradox. It is not that something is racing faster than light. It is that our intuition about separation misleads us. In the quantum world, what appears separate is often united. The distances we measure are real in terms of communication and causality, but not absolute in terms of correlation and unity. Entanglement shows that space and time, though powerful, do not define the full structure of reality. Still, unease lingers. How can unity persist across vast distances without a mechanism? How can two particles act as one when no bridge links them in space? These questions push us to consider whether our concept of locality, the idea that influences must travel through space step by step, is too narrow. Perhaps at the deepest level, reality is not built from parts at all, but from wholes that only appear divided. Relativity stands secure, its speed limit unbroken, its causal order preserved. Yet entanglement hints at something beyond relativity, a layer where unity transcends separation. It does not offer shortcuts for communication, but it reshapes our understanding of what it means for things to be connected. And so while faster-than-light messaging remains impossible, the lesson of entanglement is not diminished. Instead, it is enriched. It tells us that reality is more subtle than our categories of here and there, before and after. The speed of light rules the world of signals, but entanglement whispers of a deeper order where unity is woven into the fabric of existence itself. Physicists, determined to probe every corner of the puzzle, have pushed experiments to extremes in order to test whether entanglement really respects relativity. If two detectors are placed far apart and set to measure entangled particles nearly simultaneously, which one collapses the wave function first? Does the particle closer to the source decide the outcome, or does the order depend on the observer's frame of reference? In the 1990s and 2000s, experiments with entangled photons timed the measurements with extraordinary precision, sometimes separated by only billionths of a second. The results showed no hint of one detector taking precedence over the other. No matter how the setup was arranged, the correlations appeared instantly, and relativity's rule that simultaneity depends on the observer's frame was upheld. From the perspective of one observer, detector A might measure first. From another's, detector B might measure first. Yet the results never contradicted quantum predictions. The correlations did not rely on any particular order in time. They existed outside the sequence altogether, as if the shared state simply ignored the question of which event came first. Other experiments placed detectors so far apart that light could not travel between them in the time available. Even then, the outcomes matched quantum mechanics exactly, violating Bell's inequalities and showing correlations no local explanation could achieve. These tests confirm that the connection does not arise from hidden signals darting across space. If any such signal existed, it would have to travel faster than light, by orders of magnitude. But the no-signaling theorem tells us that no usable message is carried. Relativity remains intact, even as quantum mechanics insists on a deeper unity. The lesson is subtle but profound. Entanglement does not contradict relativity, because relativity governs the transmission of information and energy, not the correlations of a unified state. Signals cannot outrun light. Causality is preserved. Yet entangled systems reveal that the fabric of reality is not woven from separate threads, but from holes that extend across space. Relativity describes the stage on which events unfold. Entanglement reminds us that the actors may be parts of a single play, inseparable, no matter how far apart they appear. To Einstein, this remained an uncomfortable compromise. He hoped for a theory that restored locality and realism, one in which particles carried hidden instructions and nothing spooky leapt across space. But the experiments left no room for that vision. The universe is non-local, not in the sense of faster-than-light messages, but in the sense that space and time do not dictate the limits of unity. Entanglement reveals that the deepest connections are not constrained by distance. For modern physics, the coexistence of relativity and quantum mechanics in this strange balance is both satisfying and troubling. Satisfying, because it shows that two of our most powerful theories do not directly contradict one another. Troubling, because it hints at a deeper framework that unites them, a theory we do not yet possess. The dream of quantum gravity, of ADS-CFT duality, of space-time emerging from entanglement, all spring from this uneasy marriage. The mystery of how correlations can exist outside communication continues to drive new ideas about the very nature of the cosmos. As this chapter closes, one truth stands firm. Entanglement does not let us send messages faster than light. It does not overthrow relativity's speed limit. But it does reveal that separation is less absolute than we once believed. The speed of light remains the cosmic limit for signals. Yet, beneath the signals lies a web of unity that distance cannot unravel. In the next chapter, we step from physics into philosophy. If entanglement means that particles are not truly separate, then what does that mean for reality itself? Does the universe exist independently of observation, or is it shaped by the act of measurement? Do we live in a single reality, or are there countless branches, each reflecting a different outcome of the quantum dice? The answers may reshape not only physics, but our very understanding of existence. Entanglement does more than challenge the speed of light. It challenges the very meaning of reality. If two particles remain united across space, if their states are not determined until the instant of measurement, then what does it mean to say that the universe exists independent of observation? Does reality unfold on its own? Or does it crystallize only when measured by conscious observers or instruments? This question, once philosophical, lies at the heart of quantum theory. For much of the 20th century, the dominant interpretation was the Copenhagen view, named after Niels Bohr and the circle of physicists around him. In this interpretation, the wave function is not a description of what exists, but a tool for predicting probabilities. Before measurement, particles do not have definite states. They exist in superposition, a blend of possibilities. Measurement collapses the wave function, and reality takes a definite form. The act of observation is not passive. It is the moment when potential becomes actual. This view unsettled Einstein deeply. He could not accept that the moon, as he once quipped, does not exist when no one looks at it. For him, reality had to be independent of observation. Yet the Copenhagen interpretation, bolstered by experiment, insisted otherwise. In this view, asking what state an entangled particle possesses before measurement is meaningless. The state does not exist until the act of measurement brings it into being. Entanglement makes this even more dramatic. If two particles share one wave function, then the act of measuring one does not simply reveal its state. It helps create the state of the other as well, instantly, no matter the distance. In Copenhagen terms, the collapse of the wave function is global. It sweeps across both particles, pulling them into definite outcomes at once. Reality itself seems to flicker into form through the act of measurement, not locally, but across space. But not everyone accepts this view. Another interpretation, called the many worlds view, rejects the idea of collapse altogether. Proposed by Hugh Everett in the 1950s, it suggests that all possible outcomes of quantum measurements actually occur, each in its own branch of the universe. When an entangled particle is measured, the wave function does not collapse. Instead, the universe splits. In one branch, the particle is spin up. In another, it is spin down. Both exist, but in separate realities that never meet. Entanglement, in this view, reflects the branching structure of the cosmos. Every measurement is a splitting of worlds. The many worlds interpretation resolves the puzzle of wave function collapse by denying it. There is no collapse, only branching. Yet, it introduces its own strangeness. It suggests that countless versions of reality exist side by side, with every quantum event multiplying the cosmos. Entanglement, then, is not spooky action, but a sign of the branching pathways that weave together the many layers of existence. These interpretations highlight the philosophical weight of entanglement. It is not just about particles and detectors. It is about what it means for something to be real. If Copenhagen is correct, then reality exists only when observed. If many worlds is correct, then all possibilities are real, spread across infinite branches. Either way, entanglement forces us to abandon the comfortable idea of a single, independent, objective world unfolding on its own. The debate continues to this day. No experiment has definitively chosen between collapse and branching. Both interpretations reproduce the predictions of quantum mechanics. Yet entanglement keeps the debate alive, reminding us that beneath the equations lies a question about the nature of reality itself. Are we observers who bring the world into being? Or are we wanderers through one of countless worlds, unaware of the branches that unfold around us? As we stand in this uncertainty, one fact remains clear. Entanglement is real, tested, and undeniable. Its meaning, however, is still open. The universe has given us the evidence, but the story we tell about that evidence is still being written. In the play of entangled particles, we glimpse not only the strangeness of physics, but the mystery of existence itself. The tension between realism and observer-dependent reality has only sharpened as entanglement moved from theory to experiment. In the early days of quantum mechanics, the equations were so unfamiliar that many physicists treated interpretation as a matter of taste. Some accepted Copenhagen because it worked. Some favored hidden variables out of loyalty to classical intuition, and a few, like Everett, dared to imagine branching universes. But as experiments with entanglement closed loopholes and stretched across continents, the stakes grew higher. Reality itself seemed to demand an answer. Realism says that things exist in definite states whether or not we observe them. A tree stands in the forest even if no one hears it fall. A photon has a polarization before it is measured. This is the worldview that guided physics for centuries. But entanglement resists it. When two particles are linked, no description of their individual properties makes sense until one is measured. Only the combined state has meaning. Measure one, and you instantly learn about the other. not because it carried a hidden instruction, but because its state never existed separately at all. For the realist, this is intolerable. For the quantum theorist, it is simply how nature works. Observer-dependent reality, by contrast, accepts that the act of measurement plays a role in bringing the world into definite form. In this picture, what exists is not an independent state but a set of probabilities, a cloud of potential outcomes. Observation is the lightning strike that solidifies the cloud into one actual event. Entanglement pushes this to its extreme, for the cloud is shared across space. Two particles, though distant, collapse together into correlated outcomes. It is not that one causes the other, but that both are created in unison by the measurement itself. Modern physics has sought new language to describe this. Increasingly, scientists speak of information, rather than particles, as the foundation of reality. A particle state is not a thing it carries, but information about possible outcomes. Entanglement is the sharing of information across systems, so that one cannot be described without the other. In this sense, entanglement is less about spooky action and more about bookkeeping. The universe insists that the information be consistent, no matter the distance. This information theoretic view has led to some of the most daring ideas in contemporary physics. In the framework known as ADS-CFT, developed in the 1990s, space-time itself may emerge from patterns of entanglement in a deeper underlying theory. In this picture, geometry is not fundamental. It is the shadow cast by networks of entangled states. Pull apart the entanglement, and space-time unravels. Strengthen the entanglement, and space-time becomes smooth and continuous. Entanglement, in this view, is not just a property of particles within space-time. It is the glue that holds space-time together. Such ideas remain speculative, but they reflect a growing sense that entanglement is more than a quirk of quantum theory. It may be the key to the very structure of reality. Instead of asking whether the universe exists only when observed or whether it branches into countless worlds, we may need to ask a deeper question. Is the universe itself nothing but a web of entangled information? If so, then what we call reality may be an emergent phenomenon, a tapestry woven from correlations that stretch across the cosmos. This vision is unsettling, but it also brings a kind of harmony. The discomfort Einstein felt at spooky action may dissolve if we see entanglement not as influence, but as identity. The particles are not sending messages faster than light. They are not separate objects at all. They are parts of a single informational structure, revealed piece by piece when we measure them. The unity is fundamental. The separateness is illusion. As quantum technologies grow, these philosophical questions become practical ones. Engineers designing quantum computers and networks must grapple with the fact that entanglement is not a metaphor but a resource, something that can be created, manipulated, and consumed. In using it, they implicitly accept that information is the true currency of reality. The philosopher's debate has become the engineer's blueprint, and so the stage is set for the deepest implication yet. If entanglement binds particles, and perhaps even space-time, then what does that say about our own experience of reality? Are we ourselves entangled with the universe? Our choices and observations part of the same great wave function? Or is consciousness something separate, standing outside the equations? These questions press at the boundary where physics meets philosophy, where science stretches into the unknown. Entanglement has become a mirror held up to reality itself. When we peer into it, we do not only see particles bound in strange unity, we see reflections of our deepest assumptions about what exists, about what it means to observe, and about whether separateness is real or an illusion. Different interpretations of quantum mechanics answer these questions in strikingly different ways, and each carries profound implications. Some physicists favor relational quantum mechanics, a view that says properties do not exist absolutely, but only in relation to an observer. In this picture, reality is not a set of fixed states waiting to be uncovered, but a web of interactions. When one system measures another, a relationship is established, and within that relationship, definite outcomes arise. Entanglement, then, is not spooky action at a distance. It is the expression of relationships stretched across space. Each observer has their own account of reality, consistent within their frame, but no universal description exists beyond the network of relations. Others lean toward more radical views, in which entanglement is not only a feature of particles, but the foundation of the cosmos. If space-time itself can be seen as emerging from entangled information, then perhaps everything we call matter and energy is secondary, a shadow of a deeper informational reality. In such a vision, the physical universe is like the surface of a vast ocean, while the entangled connections beneath are the currents that shape the waves. What we experience as distance, causality, and even time may be emergent patterns of something more fundamental. This raises questions that touch philosophy and even metaphysics. If reality is a web of entangled information, then are we, as conscious beings, part of that web? Are our thoughts and choices also entangled with the universe, bound into the same tapestry that links particles across galaxies? Some thinkers suggest that consciousness itself may be inseparable from quantum processes, that the act of observation is not merely recording reality, but participating in its creation. Others caution that such ideas risk drifting into speculation. Yet the question remains, if entanglement defines the universe, then where do we fit within it? The mystery deepens when we ask about locality and separateness. For centuries, science has advanced by breaking the world into parts, studying them in isolation, and building understanding from the bottom up. Entanglement resists this method. It says that parts cannot always be understood separately, that their very existence may depend on the whole. This forces us to rethink not only physics, but our philosophy of science itself. Perhaps the universe is not a machine made of parts, but a network where the connections matter more than the pieces. As unsettling as these questions are, they may carry the seeds of future discoveries. Physics has always advanced by confronting paradoxes, by facing the places where our theories break down. Entanglement may be such a place, a signpost pointing toward a new framework in which information, space-time, and reality itself are unified. It may not only explain the microscopic world, but also the structure of the cosmos, the nature of black holes, and the origin of space-time. Some even speculate that the great problem of uniting quantum mechanics with general relativity will only be solved when we understand entanglement fully. In the end, entanglement leaves us with a vision of reality that is both humbling and inspiring. It tells us that what we thought was separate is deeply connected, that observation is not passive but participatory, and that the universe may be a vast web of information rather than a collection of objects. It challenges our intuition but rewards our curiosity with glimpses of a deeper truth. As this chapter draws to a close, we turn from philosophy back to the laboratory. For while entanglement stirs debates about the nature of reality, it also drives the cutting edge of technology. Around the world, scientists are building quantum networks, linking satellites, and designing computers that use entangled qubits to solve problems once thought impossible. The future of entanglement is not only in our understanding but in our use of it, in the ways it may reshape communication, computation, and exploration. The strangeness of quantum mechanics is not confined to the chalkboards of physicists. It is becoming the architecture of our future. The story of entanglement is not only about what we have discovered, but about what we are building. For centuries, physics revealed truths about the universe, and then left them to philosophy. But now, with entanglement, the truths are being forged into machines, networks, and tools. The future of entanglement research is not limited to the blackboards of theorists or the vacuum chambers of laboratories. It stretches across cities, satellites, and perhaps one day across the solar system. At the heart of this future lies the idea of a quantum internet, a network where information is not sent as streams of classical bits, but as delicate quantum states. In such a system, entanglement is the backbone. Pairs of photons or atoms are distributed to nodes in the network, linking them into unified systems even across vast distances. Messages become unbreakable by the laws of physics themselves, and teleportation of quantum states allows information to leap without traveling through vulnerable channels. The first prototypes of quantum networks already exist. In China, quantum key distribution networks span hundreds of kilometers, connecting government offices and banks, with security guaranteed by entanglement. In Europe and the United States, research teams are linking universities and laboratories through entangled photons transmitted across cities. These are small steps, but they resemble the early days of the classical internet, when a handful of computers linked together became the seed of a global transformation. Satellites play a crucial role in this vision. Fibers on Earth suffer from losses that limit entanglement distribution to a few hundred kilometers. But satellites, high above the atmosphere, can beam entangled photons across continents. The Mauritius satellite proved this by linking Beijing and Vienna with secure quantum communication, the first glimpse of a planetary-scale entangled network. Plans are underway for fleets of such satellites, constellations that will distribute entanglement globally, creating a skyborne infrastructure for the quantum internet of the future. The implications go far beyond secure communication. Quantum networks would allow distant quantum computers to work together, combining their power into something greater than the sum of their parts. They could synchronize clocks with unprecedented accuracy, enabling navigation and science at levels we cannot achieve today. They could even link Earth to spacecraft, allowing quantum communication across interplanetary distances. Imagine a future where a spacecraft on its way to Mars is not isolated by minutes of radio delay, but linked by entangled states to stations on Earth. No faster-than-light messages would be possible, but the spacecraft could still be part of a secure quantum network, its systems synchronized with Earth in ways no classical link could provide. Such ideas remain visions, but they are grounded in physics already demonstrated. The pieces exist. What remains is to scale them up, to make entanglement as robust as electricity and as familiar as radio waves. The challenges are real. Entangled states are fragile, easily disturbed by noise, heat, or loss. To build a quantum internet, scientists must perfect quantum repeaters, devices that extend entanglement step by step without breaking it. They must develop error correction methods that preserve fragile states long enough to travel across the globe. They must find ways to integrate quantum networks with the classical infrastructure we already use. These tasks are daunting, but progress has been steady. Each year brings new advances, new records, new demonstrations that the vision is achievable. The future of entanglement research is not just about communication, it is about exploration. If entanglement can link nodes on Earth, it may one day link Earth to the stars. Quantum experiments aboard spacecraft could test whether entanglement holds across millions of kilometers, across the gulf between planets, even across the vast distances of interstellar probes. In doing so, we would not only build technology but also probe the foundations of reality, testing whether the quantum unity we see on Earth persists unbroken across the cosmos. The path ahead is clear. What began as paradox, what became proof, what grew into technology, is now becoming infrastructure. Entanglement will not remain confined to the laboratory. It will spread into the networks that carry our messages, into the machines that compute our problems, into the spacecraft that carry our dreams. The future of entanglement research is nothing less than the future of how humanity communicates, computes, and explores the universe. The dream of a global quantum internet does not end with satellites distributing entanglement across continents. Researchers are already working on experiments that bring Earth and orbit into a seamless network, one that could someday extend far beyond our planet. In Europe, projects are underway to integrate satellite-based entanglement with fiber networks on the ground. The vision is to create hybrid systems, where photons entangled in space are fed into terrestrial repeaters, extending secure communication into the heart of cities. In the United States, similar efforts aim to connect research hubs with orbital platforms, building a testbed for global-scale quantum links. These are not science fiction sketches but funded programs with real hardware under construction. Deep space missions may one day push these ideas even farther. Classical communication with Mars takes anywhere from 4 to more than 20 minutes, depending on orbital alignment. For spacecraft traveling to the outer planets, the delays stretch to hours. A quantum internet extending into space would not abolish these delays, since no usable signal can outrun light, but it could provide synchronization and security that classical links cannot match. Entangled clocks could remain perfectly aligned across millions of kilometers. Quantum keys could secure communications against any conceivable form of interception, and teleportation of quantum states could allow spacecraft to exchange delicate information without vulnerable transmission paths. Already, experiments are exploring entanglement with systems beyond photons. Trapped ions, superconducting qubits, and even ensembles of atoms have been entangled and kept coherent for surprisingly long times. These systems could one day serve as the backbone of long-distance links, storing entanglement like batteries until it is needed. Imagine spacecraft carrying entangled memory banks, refreshing their links with Earth during close passes, then maintaining secure quantum channels, even as they drift toward distant worlds. To realize this future, scientists must perfect quantum repeaters that can operate reliably in orbit, shielded from cosmic radiation and the harsh environment of space. They must also develop error correction codes, capable of preserving entanglement for hours or days instead of fractions of a second. These are formidable challenges, but history suggests they are not insurmountable. Just as the first crude radios grew into the global communication networks of today, so too may these fragile experiments grow into interplanetary quantum networks. What makes this vision extraordinary is how quickly it has moved from imagination to action. Barely 3 decades ago, entanglement across a single city block was considered a feat. Now, entanglement across continents is reality, and engineers are sketching designs for constellations of satellites. The future of entanglement research is racing forward, guided by the strange unity of the quantum world, and driven by the ambition to connect not just cities, not just nations, but planets. And in that ambition lies the next great question. If entanglement can be stretched across the Earth and beyond, what limits remain? Can it reach across the solar system, across interstellar distances? If particles remain connected across cosmic scales, what does that tell us about the fabric of space-time itself? These questions will guide the next frontier of research, where entanglement ceases to be only a tool and becomes a clue to the deepest workings of the universe. The long-term vision of entanglement research reaches far beyond the blue sphere of Earth. Scientists and engineers imagine a time when entangled networks span not just continents but planets, forming the nervous system of a solar system-wide civilization. The first steps are modest, linking laboratories, satellites, and ground stations. But the trajectory points outward, toward Mars, the moons of Jupiter, and perhaps even interstellar probes launched into the dark. A quantum internet stretched across the solar system would not erase the speed of light as the limit of communication. Messages would still take minutes or hours to travel. But entanglement could provide a layer of connection that keeps spacecraft, colonies, and Earth in perfect synchronization. Clocks could remain aligned to fractions of a second, even across millions of kilometers. Cryptographic keys could remain secure, immune to any attempt at interception. Quantum teleportation could transfer delicate information without risk of exposure. Such a network would be as vital to interplanetary society as the classical internet is to ours today. Beyond technology lies physics itself. Entanglement at vast scales would allow us to test the limits of quantum mechanics in ways never before possible. Does entanglement remain unbroken across the gulf between planets? Does it persist even as signals cross the heliosphere, where the solar wind meets interstellar space? If so, It would strengthen the case that entanglement is not simply a property of particles but a principle of reality itself, woven into the very fabric of the cosmos. Some researchers speculate that entanglement might even be the key to uniting quantum mechanics with relativity. Theories like ADS-CFT suggest that space-time itself may emerge from networks of entangled states. If this is true, then the expansion of entanglement research is not just about communication and computing. It is about probing the foundations of existence. By building entangled networks on planetary scales, we may uncover clues to the origin of space-time, the nature of black holes, and the true architecture of the universe. The practical and the philosophical thus converge. The same entanglement that secures a bank's communication in Beijing and Vienna may one day illuminate the mystery of how space-time holds together. The same entanglement that powers qubits in a quantum computer may also explain why distant galaxies obey the same physical laws. The boundary between technology and fundamental physics blurs, just as it did when electricity moved from curiosities in the laboratory to the lifeblood of civilization. It is humbling to remember how quickly this story has unfolded. Less than a century ago, entanglement was a paradox scribbled in the margins of Einstein's papers. Half a century ago, it was a fragile experiment on a laboratory bench. A generation ago, it was a curiosity stretched across a city block. Today, it is a tool tested between continents and satellites. Tomorrow, it may be the foundation of interplanetary networks and the key to understanding reality itself. As we close this chapter, we prepare to step back from the laboratories and satellites, from the equations and experiments, and reflect on what entanglement means for our place in the cosmos. The final chapter will gather the threads of the story, the definitions, the proofs, the technologies, and the philosophical implications, and offer a vision of what it means to live in an entangled universe. For if entanglement teaches us anything, it is that separation is an illusion, and that at the deepest level, everything is connected. The journey of entanglement began with doubt, with Einstein raising his hand against the tide of his time and calling it spooky action at a distance. What he saw as absurd has since been tested, confirmed, and transformed into the foundation of modern physics. Across the chapters of this story, we have walked through paradoxes, experiments, proofs, and technologies, each step drawing us deeper into a universe where separation is less certain than we once believed. It began with the strange rules of the quantum world, where particles are waves of probability, and where outcomes exist only as possibilities until observed. From this world emerged the concept of entanglement, the unity of two particles in one shared state. Einstein, Podolsky, and Rosen challenged this vision, insisting that physics must be incomplete, that hidden variables must lie behind the curtain. For decades, the debate lingered, unresolved, a philosophical duel between giants. Then came John Bell, who turned words into mathematics. With his inequalities, he gave physics a way to test reality itself. The experiments that followed, from Clauser to Aspect and beyond, revealed the truth. The inequalities were broken. The universe chose quantum strangeness over classical order. Einstein's hidden variables could not save locality. Entanglement was real. From there, the story expanded outward. Entanglement was no longer just proof of theory, but the seed of technology. It gave rise to quantum computing, with qubits entangled to explore many possibilities at once. It secured communication with unbreakable keys and made teleportation of quantum states possible. What Einstein rejected as impossible became the basis of a technological revolution. The experiments did not stop at laboratories or even at mountaintops. Entanglement leapt into space, carried by satellites like Mycius, stretching across continents, and tested with light from distant stars and quasars. Across the Earth and across the cosmos, entanglement proved unbroken, a unity that distance cannot undo. And yet, the question of the speed of light remained. Did entanglement break relativity's most sacred law? The answer, paradoxical though it seems, was no. The correlations are instant, but they carry no message. No usable information outruns light. The universe respects the cosmic speed limit while reminding us that unity can exist without signals, that connection can exist outside communication. Entanglement pushed us further still, into questions of reality itself. Does the universe exist independently of observation, as Einstein believed? Or does it crystallize only when measured, as Copenhagen suggests? Do all outcomes exist in countless parallel worlds, as many worlds proposes? Or is space-time itself woven from entanglement, as new theories hint? These questions remain open, but entanglement ensures that we cannot ignore them. It is both proof and puzzle, both foundation and frontier. And so we arrive at the present, where entanglement is no longer just an idea but a resource, no longer just a paradox, but a tool. The future will see entangled networks across the globe, entangled clocks guiding spacecraft, and perhaps even entanglement stretched across the solar system. The spooky action Einstein once rejected has become the lifeblood of 21st century science. What it teaches us is simple, yet profound. Separation is an illusion. The universe is not built from isolated parts, but from connections. Entanglement is not magic. It is the universe revealing itself, showing us that distance cannot undo unity, that what appears apart is, at the deepest level, one. The story of entanglement is the story of our growing awareness of this truth. It is spooky, yes, but it is real. The tale of entanglement is not only a chronicle of physics, it is also a story of human imagination, persistence, and humility. From the first sketches of quantum theory, when the mathematics seemed almost nonsensical, to the vast experiments spanning continents and satellites, each step has demanded that we let go of certainty and embrace wonder. Einstein's resistance reminds us that even the greatest minds are bound by their intuitions. He trusted locality, the belief that influences must travel step by step through space. And for most of human history, that belief seemed unshakable. Yet the experiments proved otherwise. Aspects detectors, Clauser's photon sources, and Zeilinger's mountaintop telescopes all whispered the same truth. Reality is deeper than our expectations. In this sense, entanglement is as much a story of humility as it is of triumph. For philosophers, entanglement opens a window into questions that stretch far beyond physics. If the universe is not made of isolated parts, what does that say about our own experience of individuality? If observation plays a role in bringing reality into being, what role do we play in the cosmos? These are not idle musings, but questions sharpened by experiment. The photons and ions in laboratories force us to reconsider what it means to be real, what it means to exist, what it means to observe. For engineers, entanglement is both challenge and opportunity. The fragile links must be preserved against noise, yet the same fragility makes them perfect guardians of security. The correlations are subtle and easily destroyed, yet that subtlety makes them powerful engines of computation. Entanglement is a paradox made practical, a puzzle turned into power, and for all of us, the lesson is unity. We live in a world that often seems fractured, full of divisions and distances. Entanglement reminds us that beneath those separations lies a deeper connection. Particles born together remain together. Distance cannot undo their unity. If this is true of the smallest parts of the cosmos, perhaps it tells us something about the whole. In the glow of this understanding, the phrase spooky action at a distance takes on a new meaning. It is no longer a dismissal, no longer a sign of skepticism. It is a reminder of wonder, a reminder that the universe still holds mysteries we cannot tame with intuition alone. Spooky, yes, but real. The story of entanglement is not finished. It will continue as new experiments stretch its reach, as new theories probe its depths, as new technologies reshape our lives. But even now, at this point in the tale, we can pause and see the outlines of its meaning. Entanglement is not magic. It is nature revealing that separation is an illusion and that, at the deepest level, everything is connected. The story of entanglement has carried us from paradox to proof, from proof to practice, and from practice to promise. What began as an intellectual puzzle has become one of the defining features of physics and one of the guiding lights of 21st century science. It is a story that reminds us that knowledge is not a finished book, but a journey, unfolding chapter by chapter across generations. We have seen how entanglement began as an objection, a challenge thrown down by Einstein and his colleagues. We watched as Bell transformed that challenge into mathematics, as Aspect turned mathematics into experiment, and as modern physicists stretched those experiments across the sky itself. We followed entanglement into the realm of technology, where it powers qubits, secures communication, and teleports information. We traced its philosophical ripples, from Copenhagen's collapse to Everett's branching worlds, from relational views to visions of space-time itself woven from entangled threads. Each step revealed not only new physics, but new questions about what it means to exist. Now, as we look toward the future, entanglement promises to reshape both our understanding and our tools. It will become the backbone of the quantum internet, the lifeblood of quantum computing, the guardian of secure communication. It will guide spacecraft across the solar system and perhaps one day across the stars. And even as it powers technology, it will continue to whisper its deeper message, that reality is not made of separations, but of connections. In this light, Einstein's phrase, "spooky action at a distance," becomes a poetic epitaph to a scientific revolution. What once sounded impossible is now undeniable. What once seemed absurd is now essential. The universe, it turns out, is stranger and richer than even Einstein imagined. And within that strangeness lies beauty. Entanglement is not magic. It is the universe revealing itself, showing us that distance is not the barrier we thought it was, that separateness is not as real as it seems, and that at the deepest level, everything is connected. And so we close this story with the same mixture of awe and humility that has guided physics for centuries. Awe, because we have glimpsed a truth that unites the smallest particles and the widest cosmos. Humility, because the journey is not done. There are more experiments to run, more theories to test, more mysteries to unravel, but one truth will remain. Entanglement is spooky, yes, but it is real. And in its reality, it reminds us that the universe is not a collection of parts drifting apart, but a whole, bound together by connections we are only beginning to understand.